Hello and welcome to the Dyalog webinar. I'm Foad, the CTO of Dyalog Limited, and a bit later I'll be joined by my co-host Adám Brudzewsky. Today the subject is total array ordering. This is a new feature that we've designed and implemented for version 17 of Dyalog APL, which is due out this summer. If you're watching live on Dyalog TV, you can ask questions in the chat. We have a moderator who will handle the questions or pass them on to me as appropriate. Now, we're going to talk about grading and sorting. APL has had grade up and grade down primitives for a very long time. They take a simple array of data, so a flat array of numeric or character data, and then they tell you what order the major cells of that data should go in to have the data sorted. So if you start with the character vector APL, grade up will tell you that to put it in alphabetical order, you take the first character, A, and then the third character, L, and then the second character, P. Now when I say the major cells of the data, I mean the items of a vector, or the rows of a matrix, or the planes of a cube, and so on. So, for example, if I have a list of people's names stored in a character matrix like this, grade up will tell me what rearrangement of the rows will put those names into alphabetical order. And the result here means that row 3 comes first in the alphabetical order, followed by row 5, and so on. Now often you don't actually want this list of indices, you just want the data itself sorted into alphabetical order. So you can easily use the result of grade to reorder the rows, like this. And in fact, there are several ways of writing this. Here's one expression that I like, because it works for arrays of any rank. And this defin is actually recognised as a new idiom in version 17 of Dyalog APL. Now when I say idiom here, I mean that the interpreter recognises it specially and implements it as a whole as if it were a primitive function. And of course the same expression with grade down instead of grade up is also recognised as an idiom. And throughout this presentation I'll mostly talk about grade up, but everything I say goes for grade down as well, with the obvious changes. Now, because I like this expression, I'm going to name it as the named function sort, and in this presentation, whenever I want to sort some data, I'll use that named function, like this. Now, if you're not very familiar with grading and sorting in APL, you might try to do this. Here I have a list of people's names, N, and I want to sort them. Well, in any APL up until version 16 of Dyalog, if you tried this, you'd be disappointed to get a domain error. Why? Because grading and sorting works on simple arrays, whereas N is a nested array. It's a vector of character vectors. Well, I'm here to tell you that in version 17 of Dyalog APL, you can do this, it works, and it gives you the result you expect. So if you don't learn anything else from today's webinar, please just remember this. Version 17 of Dyalog APL, you can sort vectors of character vectors, and you get the right result. Well, actually, since the title of this presentation is Total Array Ordering, and I haven't mentioned those words yet, I should explain a bit more deeply what's going on here. Now I said that grade works on simple arrays of data. Another way of thinking of this is that when it's trying to sort in a character matrix, like the list of names I showed you before, it's trying to put the rows into an order. So the grade primitive itself is making decisions about which rows precede which other rows in the final sorted order. For example, at some point it will compare these two character vectors. The character vector Morton, which was one row of my data, and the vector Roger. Notice that Roger here is followed by a blank, was another row of my matrix. Now because they were rows from the same matrix, they necessarily have the same length. These are both 6 character vectors. Now, I say that the grade primitive defines an ordering on simple arrays of the same shape, like these two arrays. And in fact, if you start with any two simple arrays of the same shape, call them A and B, then you can use the grade primitive to tell you which order they should go in, which one comes before the other one. First I'm laminating the two arrays, and then grading the result of that. And the result of the grade here, 1, 2, tells me that Morton precedes Roger in the ordering. If it was the other way round, the result of the grade would be 2, 1. Now, I'm going to introduce a kind of meta notation at this point, which is this curly red less than symbol. Now, this is not an APL primitive. You cannot and never will be able to type it into an APL interpreter. I'm just going to use it on the slides to describe the ordering relationship between two arrays. So the last line on the slide here means that the simple character vector Morton precedes the character vector Roger followed by a blank in the ordering defined by the grade primitive. Now, the whole purpose of the total array ordering is to extend this. Grade defines an ordering on simple arrays of the same shape. We want to extend this to all APL arrays so that there is a well-defined ordering on all arrays of any shape, data type, any rank, any depth, any structure. And once we've defined this ordering and implemented it, this will allow you to sort any APL array. For example, if you wanted to sort this highly non-uniform vector, at some point the grade primitive would be making decisions about which items come before which other items in the ordering. For example, it would need to know whether the simple scalar 0 should come before or after the 2x3 character matrix Dyalog, and that is exactly what the rules of the total array ordering specifies. Now, why is it called total array ordering? Well, total order is a concept from mathematics, and it really means that given any two items from some set, you have a well-defined idea of which item comes before the other one, and that these rules are consistent, such that you can put all of the items in the set in a nice linear order. In our case, the set of items we're interested in is the infinite set of all APL arrays, so we call it a total array ordering. In fact, the ordering we're going to define isn't quite total. There are some awkward things that you can have in Dyalog APL arrays which it is difficult to define an ordering for. The most obvious example is namespaces. In Dyalog APL, a namespace mostly works like a simple scalar value, but because they're mutable and they have reference semantics, and because the user can construct arbitrary cycles of namespaces which refer to other namespaces, it's very difficult to come up with a consistent order for them that's easy to implement. We may be able to do it in future, but for now, namespaces are simply excluded from the ordering, and so are any nested arrays that contain namespaces. Now, onto the rules themselves. Now, when we were designing these rules, there were a couple of constraints that we had to work with. And the most important is backwards compatibility. We're certainly not proposing to make any breaking changes, and the grade primitives already work on simple arrays, so we had to be sure that the rules that we come up for general nested arrays, in the case where they're applied to simple arrays, still give the same results that the grade primitives have always used. And another constraint is a kind of consistency. If you look back at the Wikipedia page for total order, it said something like this as one of its rules. This says that if alpha less than or equal to omega and omega less than or equal to alpha, that must imply that alpha is the same as omega, according to some kind of equality relationship. Now, when we're talking about APL arrays, we already have a notion of equality of APL arrays, which is the grade primitive function. And because sorting and grading is and always has been intolerant, we're talking about an intolerant match here. I think I said grade, I meant match. The match primitive. We're talking about an intolerant match between two arrays, as if you had set comparison tolerance to 0. Now, this might seem like a rather obscure or trivial point, but it becomes important when you're thinking about corner cases like comparing two empty arrays against each other. For example, the empty numeric vector does not match the empty character vector in APL. So when we were designing the ordering rules, we had to be careful to ensure that there's a defined order between these two things and that the ordering rules do not consider them to be equivalent. Now, I'm going to present the rules that we came up with. I'm going to start from the simplest cases first, And the simplest case is comparing two simple scalars. And here are the rules. Comparing characters versus characters. Well, you can already do this. Grade primitives already allow you to grade character data, so the rule is the same as it has always been. And in Dyalog APL, that means that characters are compared according to their Unicode code points, at least assuming you're using a Unicode edition of the interpreter. Likewise, comparing numbers with numbers is already well defined. They're compared in the obvious way, except that we also want to extend this to cover complex numbers. Now, the rule we've come up with here is that complex numbers are compared according to their real parts, and only if the real parts match, then you compare the imaginary parts of the numbers in order to break ties. Now, this is not a good mathematical definition of less than on numbers, because it doesn't interact nicely with the usual rules of arithmetic in the way that it interacts with addition and multiplication. But for our purposes, that doesn't matter. All we need is a consistent rule that we can apply consistently to numeric data to give a consistent ordering. And similarly, if you're going to sort mixed data, at some point you'll need to compare numbers against characters, and we've come up with the rule that numbers, all numbers, precede all characters. We could have gone the other way and said characters precede numbers. It doesn't really matter. All that matters is that we have a rule and we apply it consistently. And lastly, we've included quad null in the ordering. Quad null in Dyalog APL works like a special kind of simple scalar. It's usually used to represent the absence of any useful data or nothing, so it seemed to make intuitive sense that nothing comes first in the ordering. Quad null comes before numbers, come before characters. The next simplest case is comparing two arrays of the same shape. For example, I have two character vectors here, JAY followed by a blank, compared against JOHN. And the rule here is that you proceed item-wise through the data. You compare corresponding pairs of items from the two arrays in Ravel order until you come to the first difference. So in this example, you would compare J against J, they're the same, then compare A against O, and since A precedes O, you have your answer. Now this is exactly the same rule that the grade primitives have always used for simple arrays. But in our case, we can apply the same rule to nested arrays. And the way this works is that as we proceed item-wise through the data, we use the DAO rules, the total array ordering rules that we're defining now, and we use them recursively to compare each item of the original arrays. So here at the bottom of the screen, I have two vectors of length 3. The first thing I need to do as I go through them item-wise is compare the first item of each of them. Well, the first items are themselves vectors, JF versus JD. So I use the same rule again recursively. I compare those vectors of length 2 item-wise. First comparing J against J, then comparing F against D, and because they don't match, I've got my answer. Now the next case we're going to consider is arrays of different shape, but I'm still talking here about arrays of the same rank, so I'm talking about cases like two vectors of different length or two matrices with different width and height. Now our guiding principle here is that we wanted to present dictionary order for character vectors, and by that I mean if you have a list of words like what I'm showing you here, they're sorted as follows: can, car, carpenter, carpet, cap. Which is obvious, right? But this is called lexicographical order, and again, there's a Wikipedia page for it. What it really boils down to is that if you have two words, A and B, call them, if A is a prefix of B, then A should sort before B. So, for example, taking the two words car and carpenter, car is a prefix of carpenter, so car sorts before carpenter. Another way of thinking about this is that car consists of the three characters CAR followed by nothing, whereas carpenter consists of CAR followed by something. And because of this, we often describe the rule as nothing precedes something. Another way of thinking about this is to say that content is more important than shape. And by that I mean, if you look at this list of words, the most important determining factor in how to sort them is the content of the first two, or in this case, three letters, C-A-N versus C-A-R versus C-A-T. And it's only if those first three letters match, if the content matches, then you have to consider the shape of them, i.e. whether anything follows those three letters. So we sometimes say content is more important than shape. Now, one way of implementing this dictionary order, say if you're comparing car against carpenter, is to mix the data. If you mix these two strings, the shorter one will be padded with blanks, and you'll end up with a simple array which you can apply grade to. But we wanted something that works a bit better than this for a couple of reasons. And the first reason is the blank character is not actually the first character in the Unicode alphabet, and it wasn't even the first character in Quad AV. There are some characters, or at least obscure ASCII control characters, which precede blank in the alphabet. So in the unlikely event that instead of carpenter you had another character vector CAR followed by some ASCII control codes, if you tried to mix this data and then apply grade up to it, you would find that that ASCII control code precedes blank in the ordering. So when you graded it, you'd be told that the longer string precedes the shorter string, and that's not what we wanted from our dictionary order. Another reason is that we don't just want dictionary order for character vectors, we want it to apply to all arrays. So for numeric vectors here, we want 1, 2, 3 to precede 1, 2, 3, 4. And we want neg1, neg2, neg3 to precede neg1, neg2, neg3, neg4, because it's a prefix, right? But if you approach this by mixing your data, you'd find that the shorter vector is padded with zeros, and because 0 follows neg4 in the ordering, again, you would be told that the shorter vector follows the longer vector, and that's not what we wanted from our dictionary ordering. Because of this, we came up a different way of describing what dictionary order really means. And again, I'm going to introduce a meta notation here. I'm going to introduce the idea of an item that precedes every APL array in the ordering. I'm going to refer to this as neg infinity, and I'm going to write it as this strange infinity overbar symbol. But this, I stress, is meta notation. It's not APL, it's not something that you will ever be able to type into your APL session. It's just something I'm using on the slides to describe what's going on. And the rule is that dictionary order works as if you padded your data out to the maximum shape of any of your arrays using this neg infinity element. Now I said it precedes every other APL array. You shouldn't think of neg infinity as being a number, because it doesn't just precede the numbers and the characters, it also precedes quad null. You shouldn't even think of it as being a simple scalar, because it precedes all arrays, empty arrays and high rank arrays, everything. So the rule is, if you want to compare two arrays of different shape, it works as if you had padded the smaller ones out to the maximum shape using this neg infinity. So to compare car and carpenter, you pad the shorter vector with neg infinity out to length 9, and then proceed using the rules for arrays of the same shape, which is to say you compare them item-wise, whereupon you'll find that neg infinity precedes p, because we've defined that neg infinity precedes every APL array, and you've got your answer. The nice thing about this is that it works for arrays of any rank in a consistent way. So here I'm comparing two matrices of different shape. On the left is a 3x2 matrix, on the right is a 2x3 matrix. The largest, the maximum common shape is 3x3. So the rule is that we pad both of them out to shape 3x3 using this magic neg infinity item, and then follow the rules for arrays of the same shape. We compare them item-wise, where you'll find that neg infinity precedes 3, because neg infinity precedes everything, and you've got your answer. Now the next Most complicated case is comparing two arrays of different rank. So for example, here on the left I have a character vector of length 3, whereas on the right I have a matrix of shape 3 by 5. Now the rule here is surprisingly simple. What you do is take the array with lower rank, the vector in this case, and you reshape it, prefixing enough ones to its shape to bring it up to the same rank as the other array. So I'm going to take the vector of length 3 and reshape it to a 1 by 3 matrix, i.e. a single row matrix. And now we're into a case we've covered before, two arrays of the same rank but different shape, so we know what the rules are. You pad to the largest common shape with neg infinity and then compare item-wise. Now it is possible in some cases that you start with two arrays of different rank, you follow this rule, reshaping the vector to a single row matrix, for example, and you end up with two arrays which are identical, which match each other exactly. Now if you think back to the consistency constraint that I mentioned earlier, we don't want this. We don't want to start with two arrays that did not match and then have our ordering rules tell you that they are ordered identically. So if you find yourself in this situation, the rule is that you have to break ties, and you break the tie according to the original rank of the arrays. On the left it was rank 1, and on the right it was rank 2. Now, why do we reshape by adding ones to the shape, and why do we put the ones on the beginning of the shape? Why do we prefix ones to the shape? Well, the reason is to do with visual fidelity of your data. So the display form of the character scalar A and the display form of a character vector like APL are very similar, so it makes sense that they come close to each other in the sorted order. And even more so if you compare a character vector APL against a single row matrix APL, the display form is identical. So again, it makes sense that if you're looking at your data in sorted order, these two arrays should appear very close to each other in the array ordering. So to recap, I've presented these rules from the top down, starting with the simplest case first. If you're faced with comparing two arbitrary arrays, you may like to think of working from the bottom up. So you have two arbitrary arrays A and B. To compare them, first, if they have different rank, then reshape one of them by prefixing ones to its shape. Then, if they have different shape, pad them both with neg infinity to the common maximum shape. Then proceed item-wise through the data in Ravel order, comparing the corresponding items by using the total array ordering rules recursively, and eventually you'll get down to the case of comparing simple scalars against simple scalars, and the recursion stops. Now there is one more loose end that I need to tidy up, and that is the case of empty arrays. To see why empty arrays can be a problem, consider the case of these two rank 3 arrays. On the left I have one of shape 2, 0, 0. On the right I have one of shape 0, 0, 3. Now they have the same rank, so you could try using the rules I defined before for arrays of different shape by padding them to the common maximum shape. The problem is that the common maximum shape in this case is 2, 0, 3, and this is still an empty array. So when you pad with the neg infinity items, you won't actually have added any items at all. You still have empty arrays, so you haven't made any useful progress towards a comparison. What it comes down to, if you need to compare two empty arrays, is an arbitrary choice. You need to compare the prototypical items of the arrays, and you need to compare the shapes of the arrays, but which of these two things should be considered more important? Well, when I was talking about dictionary order earlier, we had the rule that content is more important than shape. So the rule we've come up with for comparing empty arrays is that first you compare the prototypical items. In this example it would be 0 against blank. And only then, if the prototypical items match, do you compare the shapes of the empty arrays to use as a tiebreaker. And that really is the end of the rules. We've covered simple scalars, arrays of the same shape, arrays of different shape but the same rank, arrays of different rank, and then we have a special case for the case where both arrays are empty. Now, coming back down to earth, what does this actually affect in the implementation? Well, I've said this affects the grade up and grade down primitives because these rules allow you to grade or sort any APL array as long as it doesn't contain namespaces. It also affects the interval index primitive, which is this dyadic iota underscore. This is a new primitive that came out in version 16 of Dyalog APL. It takes sorted data on the left, and on the right it takes a collection of items, and it tells you where those items would occur in the sorted order of the left argument. Now, because interval index is all defined in terms of sorting and ordering, it is also affected by these total array ordering rules. And the effect of this is all three of these primitives, grade up, grade down, and interval index, can now work on arbitrary nested arrays. Now, in a minute, I'm going to hand over to Adam, who will show you some examples of how you can use this stuff in your applications and some things that you can do with this that were impossible or at least very awkward to do before. Before I hand over, I'd just like to thank some of the people whose work I'm presenting today. The total array ordering is an idea that we stole from the J programming language. J has had a total array ordering since about 1996 when Roger Huey implemented it at the suggestion of Arthur Whitney. And then more recently, Roger started advocating for implementing something similar in Dyalog APL. At that point, John Scholes came up with an APL model for the comparison of dialog arrays, and you can see this in the dfns workspace and up on the dfns website. Then last year, Roger Huey started implementing these rules in the C in the Dyalog APL interpreter, and this kicked off another intense round of discussion. I have something like 400 emails in my inbox relating to this, and instrumental in that discussion were Adam, who insisted that we should have dictionary order for character vectors, and Roger and myself and John Scholes and Morten Kronberg. And now I'm going to hand over to Adam for the demos. Thank you.
Thank you, Jay. Okay, let's use this. I'm going to load in a variable that contains a phone book. Here's my phone book. It is a rather complex array. It is a matrix, and the first column contains character vectors, and so does the second column. The third column contains numeric scalars, as can be seen by the box display. We're going to define the function that Jay likes. You can see that it turned yellow in the background. This is the interpreter recognizing right away that we're dealing with an idiom. And now we can sort the phone book, and it just works. D, F, R, S, it is in proper order, and where there are duplicates, like here, and the second column also has a duplicate, then eventually we end up sorting by the numerical order of the third column. So, let's save that. Now we have our sorted phone book. And as Jay mentioned, if we have a sorted phone book, then we can look with the interval index primitive where things belong there. So now we have a new record that we want to insert into our phone book. So we can ask, given this sorted phone book, where does the new record go into this phone book? And it tells us it is in the second interval. So going up and looking at our phone book, this is the first interval and this is the second interval. Indeed, that fits because K comes between F and R. So now we can insert it. We're going to take the records that are before the new element. We're going to insert the new record and we're going to append at the end all but the ones that precede from the phone book. And that gives us a new phone book with the new record inserted in the right location. We can make this into a neat little train because we have the same argument for take and for drop. So we put 2 on one side and the phone book on the other side, and we're going to have the take of 2 of the phone book. We're going to insert the new element and we're going to have the drop of the new element. Lessen the font size a little bit so we can see more. And we can then take this whole thing and build it into a utility function which inserts records into an existing sorted phone book. So we're going to have the interval index of the new element into the phone book, and we're using that as the left argument to this train. With the actual phone book on the right. And now we can have new phone book, a new record into the existing sorted one. And there we go. Okay, on to the next example. Here is an Excel spreadsheet in Excel. I'm going to take the data from here and I want to copy it into APL. So I'll copy it to the Windows clipboard. And I'm going to store it in this SS variable for the spreadsheet. For that, I will create a new clipboard object, just long enough that I can get out the corresponding array value from there. And here we have our spreadsheet. And of course, with our sort function, we can sort the spreadsheet. It is a quite complex array. It's a matrix representing a spreadsheet. We have dates being represented as quad-TS style numeric vectors. We have character vectors for text data in the spreadsheet. And we have numeric scalars, as seen here by the display. And we have quad nulls that represent empty cells. But still, we can sort this. And we can see that we put nulls on top as J specified. And then we have our numeric vectors. And then we go to the second column, of course, for those that are identical in the first column, we're sorting them alphabetically by the second column. And we can also, of course, go and specify which columns we want to sort by. So we're grading by column 1 and column 3. And then we're going to use that to index into the spreadsheet itself. And now we can see that we have sorted first with the quad null on the first column and then the dates in the order. And then over on the third column, we can see that these dates that are all the same, null comes before numbers, and these two that are the same, numbers come before characters. Of course, nulls before everything else. right? Let's look at another example. Here is Windows Explorer showing a folder with a bunch of files of various names. These names are currently in a rather random order, but I'm going to tell Windows Explorer to sort them by name. This looks fine, but if we look really carefully, we'll see that there's a name here, my10, and it comes after my2. This of course makes sense because 10 comes after 2. But really, if we were to look at the names character by character, then after the y, where they're all identical, we proceed to the next character, which is a 1 here, a 2 here, and for the 10 it's a 1 again. And we know that 1 sorts before 2. So what happened here was that Windows did something called a natural sort, which is a sort order that makes more sense for humans to look at. And what it does is it takes out runs of digits and it compares them as actual numbers against each other, at which point, of course, 2 comes before 10. Let's do this in APL. So here's our variable containing a vector of names. They are in fact the same names that we saw in Windows Explorer. And our strategy here is going to be identifying the runs of digits and converting them to numbers so that we can compare numbers properly with each other. First step in that is to identify the digits. So digits is anything that is a member of the set of digits. So quad D is just a character vector of all the digits. We can try this. So we can see 1 and 0 are indeed digits. Next step is going to be finding where to split this character vector into its pieces. So trying to find the cutoffs. First we start with a 1 because the first character always begins a new section. It doesn't matter whether it is a character or a number. And then we're going to do the pairwise on whether the argument has digits in that position or not. So this tells us where we're going to split. Let's try it. We can see correctly that we're going to begin a new section, a character section, a letter section on the M, and the Y just belongs together with that. And we begin a number section with the 1, and the 0 belongs to that, and then the B is by itself as a letter again. So now we're going to define a function which cuts into parts. And that's going to take the cutoffs of the argument and partition using that, and it's going to partition the argument itself. Let's try it. The parts of my10b, and we can see we have correctly cut my10b into my and 10 and b, but notice for this display form that 10 is still a character vector, not a number. We have to do something about that. So we are going to define a function that we can apply to each one of these parts, so that will convert those that represent numbers to actual numbers. So in other words, we're going to execute the numbers. We're going to do this conditionally. If it's true for all the characters in a part that it consists of digits, that they're digits, then we're going to execute it. Normally we would be afraid of using execute on user data, but here, since we're absolutely sure that the input is just digits, then it's safe to execute. And if it's not just digits, then we're going to leave it alone. So we can try this. We're going to execute those pieces that represent numbers of those parts. And now we can see that 10 has indeed been converted from a character vector to a numeric scalar. So let's try using this on all our data and see how it turns out. So we're going to glue exegnums each together with the parts so that we can take this entire thing and apply it to each one of the names. And let's stack them on top of each other so that we can see what's going on. And now we can see that things have been cut into the right pieces. And we are going to compare eventually the first part, which is a character vector of these names, with this numeric scalar down here. And of course, our 2 is going to be compared with a 10, and 2 will go before 10 in the correct order. Doing this without total array ordering would be very difficult, because we need to preserve that the numbers are indeed just scalar numbers and not characters. We need to be able to distinguish them and still sort them correctly. So now we can define an ordering function, which is going to be the grade of this exegnums each on the parts, and then that whole thing applied to each one of the argument. So this order function becomes a stand-in for grade that defines a new order, which is a natural order. And with this, we can get the indices that we need to get, and therefore we can define our net sort function, which uses the same kind of expression as we have used before, but now we use the order drop-in instead of using just grade. And here's our natural sort function. Now we can do a natural sort on the names. And let's compare this to the result we got in Windows Explorer. And we can see that the order we get here is exactly the same order as we got with our net sort function. So, in summary of this, I'm going to use a little enhancement to the defs user command that's also coming in. This enhancement is also coming in version 17, and that gives us a top-down view of all the one-liner functions that we have in the workspace. So here is everything that we have defined. NetSort calls order, and order uses exegnums and parts, exegnums uses digit, and so on. This is what you can look forward to in version 17. You can grade and sort pretty much any array. You can use the new sorting primitives that are super fast for arrays of all ranks. And of course, you can use the total array ordering for grade up, grade down, and interval index. If you have any questions, please let me know. Otherwise, I say thank you for watching this webinar, and hope to see you back in future webinars. The next one around is going to be with Morten Kronberg on APL processes and isolates and doing things in the cloud. Notice that because of daylight savings time change, then the UTC time is going to go backwards 1 hour, but the UK time stays the same. Right, so we have a question as to the total array order, the natural sorting order that I defined only works for positive integers. And indeed, if one was to go online and look at what's written about natural order, it is not an exact science. How exactly should we handle negative numbers, and how do you handle decimals and complex numbers and so on? Can also be numbers with exponential format, and there are various approaches to it. There's no one rule, but of course it could be defined in an extension of this. One could use a pattern matching, for example, to identify pieces of the character vectors that are numbers. But for each purpose, of course, one will have to to define the exact code for it. Right, so thank you very much for watching.